All right. Okay, so anyway, so what we were talking about before is what if we took our 4 cores and we gave them each a fourth of the memory, and we had this, but each one was hard coded to one of the fourths for speed, right? Because what we're trying to do here is we're trying to maximize speed, maximize bandwidth. Because we've decided that the communication between a single core in our CPU, and the memory it's attached to is limited as to the slower of the two. Well, if you're sharing a single 3 gigahertz RAM bucket, or RAM stick, with 4 cores, you're only getting 0.75 gigahertz of download speed or transmission speed from that RAM stick to each core. So what we can do is we can say, well, let's split our memory into fourths. So we have 3 gigahertz, 3 gigahertz, 3 gigahertz, 3 gigahertz. So now we have this 2.8 gigahertz chip talking to this guy. We can even say these are 3 gigahertz. So there's no downside here. There's no downside here. There's no downside here. There's no downside here. But the real downside then becomes when this guy needs something from one of these other memory banks, he has no way of getting to it. Okay? So how can we fix this problem using other technology using other technology as a reference?
My only thought that I came up with was like if you had like some sort of traffic controller that delegated what goes to like each memory. So it's not each memory stick isn't hard coded into each one, but like it's supposed to go to each core. Like so first memory stick goes to the first core. But essentially it goes through this like a traffic controller or something, and I don't know how this would even work. You have to be able to process a massive amount of memory really quick.
Okay, so you want to have something that lives between the RAM sticks and the CPU cores, right, that only gives one of those resources to one of those guys at an individual point in time. Mm-hmm. So I guess if we're talking about like a network technology, this would be like a load balancer. So he's only going to give resources to one of the RAM sticks at a time, so you're still not dividing up the 3 gigahertz, right, but you'll at least let the guy who needs the data get the data.
Right, and I guess like my thought is maybe we have something that can go that fast, because it's going to have to be doing like 4 times the controlling to figure out where everything's going. But I mean, if that's the only job it has, we could probably get that going pretty fast.
Yeah. So when I write the word RAID up here, what does that mean to you? As it relates to technology.
Yeah. I think
Is it load balancing? How? Oh, so since I said that, you decided this must be related? Yeah, okay. It's true. Okay. How many of you have heard of RAID technology before? All right. What is it?
Redundancy array.
it's like a sorting array. Yeah.
Redundant.
It takes multiple arrays.
What's it relate to? What part of the computer does it relate to?
Array. Yeah. Like it's a data.
It's a hard disk.
Your hard disks.
Yeah.
Okay. So the idea with a RAID is if you want to get, there's different levels of RAID. You have like RAID 0, RAID 1, RAID 2. So it deals with redundancy as well as performance. So it's a balance between those two. So if we just talk about our version of RAID here, what if, let's just say we'll keep our full 16 gigs, all right? But we'll actually buy 4 16 gig sticks, okay? We're just throwing more money at it. We'll just say it's not a problem, okay? We obviously now have the issue of making sure we have a motherboard that can take that much. So we're reliant on some of those. So it's going to be more money then too. But let's throw the money out the window and say that's not the issue, okay? So now I have 16 gigs, 16 gigs, 16 gigs, 16 gigs, each at 3 gigahertz. And we're going to say each of these cores, is at 3 gigahertz. Each core is hard-coded into one of these sticks. Now, the person who's in, well, the subsystem that's in charge of loading things into RAM is going to be the memory manager of the operating system. If we were to create a RAID setup for this, what we can do is we can have every single time something gets loaded into bucket 5 of this memory stick, it also gets loaded into bucket 5 of this memory stick. It also gets loaded into bucket 5 of this memory stick. It also gets loaded into bucket 5 of this memory stick. So we will make sure that at any point in time, all 4 sticks are duplicates of each other. So reading and writing from one is just as good as reading and writing from any other one. Make sense? So every read, every write happens 4 times, but reads and writes are very quick. Actually, I'm sorry, every write will happen 4 times. A read only happens once. So writing stuff into memory will be slower, okay, because it has to be written into 4 separate things. But because it's being written into 4 separate things, it's not really that much of a bottleneck, because it's just the time it takes to write to 4 different resources. We're not writing to one resource 4 times. We're writing into 4 resources each one time.
Oh, okay.
All right, so it's not that big of an issue. So now what you have is whenever this guy needs data, he can get that data from his single hard-coded memory stick that's dedicated to him, because all the memory that's in all the data he might need to get is there, because it's duplicated across all 4 of these sticks.
And it's not like the memory of each stick is the problem, because originally we had just 4 gigabytes, or say 8 gigabytes per stick for that one RAM stick, but now we've got 8.
Or 16, whatever it is. Yeah,
So
yeah.
essentially,
You've quadrupled the total amount of RAM on your machine for 4. If we're trying to maximize for 4 cores, you've quadrupled the total amount of RAM on your machine, but your usable RAM is only a quarter of that, because you're duplicating RAM 4 times.
Gotcha.
So this would give you the maximum performance, right?
Yeah.
Throwing money out the window. Not because really the main problem with this is not the cost of those RAM sticks. That's not that prohibitive today, right? RAM's pretty cheap. You get 16 gigs of RAM for $100, whatever it is, something like that. Okay, so that's not that big of a deal. But if you go out, so when you were shopping for motherboards, so you probably got a decent gaming motherboard, something like that.
Yeah.
So you would probably pay what, like $130?
Yeah, 129.
Something like that, yeah. All right, so that's like a pretty good motherboard, not a budget pleaser. But if you were out there looking for like server motherboards, you probably saw motherboards that were $400 or $500. Okay, what's the difference?
More RAM.
Well, several things, but they could hold more RAM. Some of them will have 2 CPU slots. So now you have dual quad cores or dual 6 cores, that kind of stuff. So the more hardware you get onto a motherboard, the more technology is going into it, the more expensive the board tends to be. So now you're talking about somebody building this, performance board, right? That has 4 different, maybe has 8 different memory slots. That way you can get, enough chips in there to build up your stuff. But it has, 8 memory slots where every 2 is dedicated to one of the cores on the CPU. And this is assuming a quad-core CPU. If you wanted to support a 6-core CPU, now you're going to need 12 memory banks. That make sense? All right.
Unless you had 2 extra cores that just jumped in to help wherever was needed.
We already have that, because now you have those 2. I mean, the process scheduler for the CPU scheduler for an operating system, its whole job is to keep the CPU as close to 100% busy at all times. So we're already beyond this idea of segregating these 4 guys to individual tasks. All 4 of these cores are going to they're going to jump in with whenever something needs to be done. And they're hard-coded to a bank of RAM. That bank of RAM just happens to be a duplicate of all the other banks of RAM. So they have all the data they need in their own dedicated resource. That makes sense? So you would effectively need a custom-built piece of hardware that was made for the CPU you happen to put in there in terms of number of cores, so that you had, effectively a hardwired communication channel between that RAM bank and the core on the CPU. At the same time, you'd also have to have a link between the 4 RAM banks, so that all writes went to all 4. So everything was done in quadruple. Does that make sense?
Yeah.
So a lot of specialized things, but not impossible. That's a doable thing, right? Why don't we do it?
Money.
To an extent. Do you think some of those server motherboards kind of do some stuff like this?
Yeah, probably.
That's kind of their point, right? They're meant to have higher performance. They're meant to do some other things like that. So those server motherboards, when you're paying a premium for them, and you're asking yourself, well, why is it more expensive? They might not do this exact thing, okay? But some hybrid of this that makes it affordable, at the same time comparable to, you know, the performance. But, you know, we also have one other problem. If our motherboard can be of unlimited size, no big deal. And technically your motherboard could be of unlimited size, but we have ATX standards for cases. So there's typically a maximum size a motherboard can be before it will no longer fit in the large cases, the full tower cases. So if you're going to rely on a company to build a one-off anything goes motherboard, all of a sudden you've decided I'm also needing one-off anything goes tower. Okay, so by the time everything's said and done, you have a 15-foot tall by 12-foot wide tower to house this gigantic motherboard that can deal with 4 8-core processors, where each processor gets its own memory bank that can hold up to 64 gigs of RAM, that kind of stuff. So you start seeing where it becomes very customized, very one-off, very expensive, and that trade-off maybe isn't worth it for consumer computing. Now, for specialized supercomputer type things, maybe it does make sense. Okay, it's kind of makes sense how memory works then.
Yeah.
Okay, so we have this one resource that's being shared by a bunch of cores, and that one resource can only make one thing completely happy at a time. And if it has to start sharing its resources, now the memory manager is going to probably try to limit how many things access RAM at once. So the reality is at any point in time, each core will be getting 3 gigahertz of performance from the RAM. But they can't all access the RAM at the identical time. The RAM will be protected by some sort of bouncer that will make sure only one person can grab that resource at a time, or if 2 grab it, it's with some constraints, something like that. Okay, so what's the role of cache memory? If we go back here, even in the most ideal situation here, okay, so we've created this perfect computer. Money didn't matter, right? Each core has a dedicated memory bank. Okay, if we just dumb this down, just to simplify let's say only have a single core CPU with a single memory bank.
And it can be bottleneck.
These are the same speed, 3 gigahertz, 3 gigahertz.
Every time we have to go to RAM, processor RAM.
Is that okay?
Not only because cache can temporarily, whatever the reason the access memory can store, it can hold cache.
Okay, but what's the benefit of cache?
Instead of going to a RAM, we can directly take from the cache memory processor.
So you're saying cache is faster. But does it matter? If this guy can only read at 3 and this guy can give at 3, do you need something faster? Having cache that can serve stuff at 100 gigahertz.
What if it's having to write something? The CPU does calculation, has to write back to RAM instead. Can it write to that cache?
But try not to get into those little specific one-off examples. I mean, the idea here is that we have a CPU that's operating at 3. We have RAM that's operating at 3. These guys are synced, right? I don't need something in the middle that's any faster because this guy's already getting the maximum speed he can get from this.
Oh, okay, yeah.
That make sense?
Yeah.
But now, the second I throw, here, we'll just keep our single RAM in here. Sorry, I duplicated the wrong guy. So now we have a dual core processor. Now, these guys are only getting half performance from this RAM. So by adding in some cache memory that sits, we'll just physically say it sits between the CPU cores and the physical memory. And we're going to say that this guy is a lot faster. Okay? Really doesn't matter what the number is. It's a lot faster. And it'll be a lot faster than the CPU is. Because we're already seeing that the CPU speeds are, we're already seeing that the CPU speeds are close to our RAM speeds today, right? There isn't a drastic difference, okay? So we can look at what's the actual speed of like here, actually, let's just do a quick search. Speed of L1 cache. You're going to give me a... Let's see if this guy will give me a speed thing. Yeah, I'm not getting a great... I mean, it's a fraction of the speed of RAM. Okay? It's way faster. Way, way, way faster.
5
All right.
gigahertz?
Huh?
5 gigahertz? Does that sound?
I think L1 cache is going to be a lot faster than that. Okay, but regardless, and actually that would even be enough. 5 gigahertz would actually be enough for this example. But punchline here is that cache is faster than this. As a general rule, we would say that when we talk about memory, let me just throw a slide in here. I think we've even mentioned this before. The closer to the CPU the memory is, the faster and smaller it tends to be, and more expensive. Okay, I think we said something similar to that in class, right? Earlier when we were talking about how expensive memory used to be, several classes ago. All right, so if we have this model here, where we have cache in the middle. Now, look at this thing. The closer to the CPU the memory is, the faster it is. So we're saying cache is faster than RAM. And the smaller it is. That's kind of the catch here for us. So this guy is faster than this guy. But for right now, let's just call this guy, we'll just deal with the fastest. So this is L1 cache. Okay, we have L1, L2, L3 cache. All right, and we'll talk about the differences either in a few minutes or next time, whatever. For right now, that's not the issue here. L1's the fastest, so let's just deal with the extremes. Okay, relatively speaking, this guy's a lot slower than this guy, but this guy's a lot smaller than this guy. Okay, this guy might be like 32 kilobytes or 64 kilobytes, where this guy is 16 gigabytes. So clearly, we can't store all this crap in this. It won't fit, right? So all the benefits we get from this guy from a speed perspective now has a caveat. Is the thing that this guy needs from memory currently here, or is it here? Does that make sense? So this guy can only hold a fraction of what's here. If we just keep these numbers simple, let's say that let's say this can hold 500 things. Let's say this can hold 5 things. Ratio is probably not correct, but let's just say that's what it is. All right. So when this guy says, I need something from memory, he's going to first go and look in cache, L1 cache. Now, what's nice here about L1 cache, so we'll go ahead and cover this piece, is that each core gets their own version of that. So L1 cache is on a per core basis. All right. L2 cache is also on a per core basis. L3 cache is shared among all the cores.
Are they all the same size?
Um,
The caches get as
They would be all. They would be the L1 cache would be the same size on a single processor, but some like more expensive processors tend to have larger L1 cache.
Okay.
That's the thing that drives the price. The more L1 cache you have, the better performance you have, as we're going to talk about here in a second. But that's really fast, really expensive memory. So if you're going to put a lot of that on there, price goes up, right? So it's kind of the deal. And go back to this slide here. The closer to the CPU the memory is, the faster and smaller it tends to be, which means as we get farther away from the CPU, if we want to just kind of, we want to draw the infrastructure here. So there's our L1 cache. In fact, actually, let's oh, that was terrible. I'm going to draw them kind of to scale here just so we have a visual. So there's their L1. Let me actually... Here's our L2. I'll just take the word cache off of there. And we'll make that guy green. There's our L3. That's still probably not to scale, but system RAM. So this is RAM at 3 gigahertz is huge compared to L3, which is shared amongst all the cores, compared to L2, which is bigger than L1 but smaller than L3, which is a lot smaller than RAM. And L1 is the smallest and the fastest, and that's closest to the CPUs. This kind of makes sense? Okay. So, in our model right now, let's just deal with L1 cache. Okay, because the reality is L1 cache kind of came first. L1 cache maybe has gotten faster over time, but the initial idea of L1 of cache started off with L1 cache. Like, let's put this really fast memory, relatively speaking, right next to the CPU, right next to an individual core on the CPU. And to make it cost effective, we're not going to be able to put very much on there. But now what we're going to need to do is we need to put the stuff in this memory that we think we're going to need next. So now we're dealing with guessing, predicting what stuff from RAM we're actually going to need next. This makes sense? This kind of sounds familiar to what we talked about earlier with the whole paging algorithm for virtual memory. We were swapping stuff in from real memory and virtual memory to make sure the stuff we need soon is in real memory. So now we're saying the stuff we need even sooner should be in cache. That makes sense? But the issue here is we have a very small amount of L1 cache. So because we have a very small amount of L1 cache, we have to have some sort of algorithm in place that makes some pretty good guesses as to what makes its way into L1 cache versus what gets to stay in system memory. Make sense? All right. So when a CPU says I need something, the first thing he'll check, this kind of is related to like programming. All variables resolved through the most local definition. So if this guy is looking for a certain value, he will check his most local scope, which is L1 cache here. If he doesn't find it there, let's we'll fill in the blanks here. I really want to talk about the example of just L1 cache existing with just system RAM. But if he doesn't find it there, he'll look in L2. If he doesn't find it there, he'll look in the shared L3. If he doesn't find it there, he looks here. That sounds pretty similar to how programming works for resolving variables. Okay? So, but we'll just talk L1 and system RAM. So when he doesn't find it here, it's called a miss. Okay? So he tries to do a lookup in L1, doesn't find it, he misses. What's the fallback plan? Go and get it from system RAM. All right? So the idea is that at least some of the time, you're going to be able to grab the next instruction, the next piece of data you need very, very, very quickly from L1 cache. The rest of the time, you're going to have to go and pay full price to get it from system RAM. Okay. Now, the idea here is that if at this point, if we're just abstracting this, we're saying that you're effectively reducing the number of times you have to hit system RAM, even if you're just reducing it a little bit. The less time you have to hit system RAM, the more often system RAM will be able to operate at its full speed. That make sense? So you're kind of cutting into the problem. Okay? Same thing's true here. When we move to L2 cache, now we're increasing our odds even more. Because now the idea would be if we have both L1 and L2 cache, L2 being still a lot smaller than system memory, it's still way faster than system memory, and it's only a little bit bigger than L1 and a little bit slower than L1. This is all relative, right? Okay, so we'll look at our fastest place first, hope for the best. Look at our next fastest place, hope for the best. Look at our next fastest place, hope for the best. Fall back to this guy, who will then look for virtual memory to grab stuff in. So we'll have this pool of virtual memory on the back that's just super, super slow. That makes sense? All right, so why is it that we stop here? So notice the kind of the architecture here for the caches. L1 and L2 on a per core basis. L3 is shared among all the cores.
At a certain point, it's not necessarily faster, so or they're not necessarily going to need to use every single cache. So maybe only core 0 needs to use one at that point.
Okay, well, so on one hand, even though we're not talking about it in real detail, there is overhead. When we have to search here and don't find it, when we have a miss, that costs us something, right? A little tiny piece of time, but time does add up, right? So when we have a miss here, that cost us something. We looked for something in room 1 and didn't find it. We would have been better off had we not looked for it in the first place. Then we looked for it in room 2. If we didn't find it there either, we would have been better off to not look in either of those rooms. But we did. We spent the time to look in there. Okay, then we'll look in room 3. At some point, there's going to be this diminishing returns, right? Where we're like, look, I have L400. So to the point where L401 is system RAM. L400 is just a little bit faster than system RAM and a little bit slower than system RAM. Okay, so you have all these different little levels that you have. And you get to the point where you now have diminishing returns because the amount of time it takes to check and then say, oh, I missed and now I need to go check someplace else adds up to more time than you were theoretically going to save. Make some sense?
Yep.
All right. So these guys are all substantially smaller than what we have on here. Sometimes you might have an L3 cache of like 100 megabytes, something like that. You might have an L2 cache of a couple of megabytes. Even 100 megabytes for L3 is pretty big, but let's just use those numbers as rough things. So you're talking probably something like 32K, 1 megabyte, 25 megabytes. Something like that. Okay? With probably similar drop-offs in speed. All of these guys are going to be faster than this memory, but they're going to be a lot smaller and a lot more expensive per bit if we want to break it down to that level. All right? So the purpose of cache is to hopefully smooth out the performance. These aren't fixes, right? So we kind of think of it, again, I mentioned a word earlier. and this is something that is prevalent throughout computing, and it's this idea of trade-offs. We're constantly making trade-offs in computing. We're often trading speed for cost, or speed for heat, things like that. We want it all, but getting it all becomes problematic. Okay, we want the fastest processor for the cheapest price with zero heat. That doesn't exist. It would be awesome if it did, but it doesn't. Maybe it will. Sometime in the future, maybe memory will just be free. Just, it's literally growing on trees. The whole thing is money growing on trees. It's literally memory is growing on trees. They're having a RAM tree. Okay? And it's infinitely fast, so you don't have to worry about access time. It's no heat. In fact, it's cold. Okay? You got to wear gloves to handle it while it's being used. Okay? Because it's so cold. All right, so we're often making trade-offs, and usually those trade-offs is leads to what's going to give us the best average performance up against cost. Where are our priorities? Okay, and this is no different than humans make in real life. Okay, we even look at a car. Will any car that reliably turns on get you to work? Sure. Why do some people spend $100,000 on a luxury sedan versus $25,000 on a Chevy Malibu? Is it? I'm not sure luxury sedans would necessarily be substantially faster. Maybe a little bit. Comfort, poshness, whatever, status symbol. So there's different trade-offs for people, right? So somebody might say, I'm going to drive a Mercedes because maybe they think when they go meet with clients and whatever their profession is, it makes them look better, that kind of stuff, whatever it is. So they're trading off. They're deciding I'm going to spend more money for something that is giving me more performance in a certain way. Maybe it's faster. That's maybe buying a sports car, right? You go out and you buy the Ferrari instead of like a monster truck. You might spend the same amount of money, but it's like, look, I care about crushing buildings, not speed. So in daily lives, we're constantly making trade-offs. What's our highest priority right now? Things like that. The same thing exists in technology. If we didn't have fixed sizes to our hardware, if anything would fit in any ATX case, if the motherboard didn't have a limited size, if we didn't have a standard socket size for the CPU, all of these things that kind of streamline the manufacturing process, which also then drives the price down, right? If every CPU was a different size, wouldn't motherboards and CPUs probably cost more? Because we wouldn't have a standardized production process? Yeah, they would cost more. Consumers don't like things to cost more. We want it to be fast and cost less. So that's where we start getting stuck into standards. And standards are good for us historically. Because earlier today we talked about non-standards. When we used to take a floppy disk into a lab, and if you put that floppy disk that was formatted on a PC into a Mac, it would want to ask you if you wanted to format the disk. It won't run in that machine. Make some sense? All right, so important punchline for us here is cache does not solve the speed problem. Cache smooths out the downside. Cache reduces the amount of time that RAM is being shared between multiple cores. Even just a little bit. Because you're going to have misses. You're going to look for something in your cache and not find it. And when you don't find it, you ultimately got to go to the main resource. All right, make some sense? Mm-hmm. All right, so now let's look at our book and come up with some really hard homework. Does that sound good?
Sounds good.
Sounds perfect. That's exactly what I was looking forward to. So we're going to look in So I want you to read through 5.1 and 5.4. Here, let me actually create the assignment in here because I'm going to have you put some stuff in here too. Access is denied. Everybody's turned in their hackathon penalty stuff.
I had a very, very, I'm telling you, I had a very good selfie. And I happened to show it to my family and they were super shocked.
All right, so I'm going to add a new, let's see, this is homework 6. We liked the hackathon. It was a good experience. Did you like doing mobile better than VR?
Yeah,
We are better.
at least, yeah,
I
for me.
felt like I was able to help more in VR, just because it was like I could figure out how to map things. So that was
Okay.
nice.
Okay, so I want to read and complete interactive exercises for 5.1 through 5.4. What's the right ones, right? Yes, so not 5.5. We'll start talking about this next time. So 5.1 through 5.4. Then I want to go down here.
You do? You paid that much for 4 terabytes of solid state memory? I can't pay that much. I'm not done. The 2.
All right, so let's do exercises at the end of the chapter, all the exercises from 5.1 through 5.5. And some of them have subparts. So like 5.5.4, 5.5.5, things like that. So do everything up to, but not including 5.6 on at the end of the chapter. All right, so that's exercises 5.1 through 5.5. Exercises at the end of the chapter from 5.1 through 5.5. Do everything, let's see, do all parts of each and stop before 5.6. All right, sound good?
Sounds good.
Let's do 6 o'clock on the 26th. Okay, questions, comments, concerns, bribes?